The next drawing that we will extract from what we have learned is what is called the vapor pressure curve. And what we are plotting here, and this plot is with you in your notes. This side is pressure, this side is temperature. And we will translate the same diagram into this form as what are the states that are possible for a pair of pressure and temperature specifications. This diagram ends up getting one line from these lines. What you see here is that at 1 bar the saturation temperature was this much. At 10 bar the saturation temperature was this much. 100 bar it was this much. So in the saturated state between critical point and triple point, this is temperature, this is pressure, and this will be vapor, this is liquid. Okay, so this line represents states where there is an equilibrium between solid and vapor. So you heat it this way, there is sublimation. In this case, any process that goes from left to right is vaporization. Across this line is condensation. Only one line remains now, the line between liquid and solid state. And here we get two types of lines. One, a line that can either go this way or a line that can go that way. And the slope of these lines are pretty much close to 90 degrees. Very difficult to make out any difference there. So these are two different types of substances. This is a substance that contracts on solidification, and this is the one that expands on solidification. So these lines represent the lines where you have equilibrium between a solid and a liquid state. Okay, so this tells us in a nutshell all types of states that are possible, and this vapor means this is superheated vapor. This liquid means it is a subcooled liquid, and just solid in this. And this line is saturated states. All saturated states. That's the vapor pressure curve, and the way it actually looks like, it is there in the notes with you. Okay, this one. So this is the actual part for water, and you can see the scale here is in degrees Celsius. This side is pressure, logarithmic scale, 0.01 kilopascal to 1 lakh kilopascal. This line, this is the saturated line, liquid vapor line. These points are solid liquid lines, solid vapor line. And this is ice or solid ice on this side, solid phase, and here there is liquid phase. So you can see that actually what I have drawn is again quite an exaggeration just to bring out the point. The fact is that this line is very steep, and for other substances also this line will go slightly back. It's not going to be very much different from this particular line. So it's not like they are curved at very sharp angles like you see here. Okay, so this is the real thing, that what it looks like, a chart. So now we have a complete handle on liquid, vapor, saturated states. we now need to look at how we can construct a bigger picture out of this. For instance, if we take this picture and say, look, now I will, instead of making it on two axes on a piece of paper, I will make T, V, and a third axis normal to the paper, which is P. So you have an XYZ system, and every state point can be located uniquely in that state. And the reason we do it is simple. Because from experiments, we measured P, V, T. And now we try to make a plot. And okay. Pressure here, temperature there, and specific volume over there. And what we are doing is a simple thing. We got lots of data from different researchers across the world over the last 70, 80, 90 years of P, V, and T. And that's the only data we have for thermodynamic properties. And we plot it on this curve. So it will make a 3D surface. And this surface looks a little bit complicated. And I showed the first one here. This is in the notes. This is temperature. This is specific volume. This is pressure. And what we had been drawing was T versus V. We now show it here that every horizontal slice is T versus V at that pressure. So we have stacked up those curves one over the other and joined them by a three-dimensional surface. So you get an inclined surface, which is the solid vapor phase, triple line, a critical point which has this shape, and as we go up and keep taking slices, this TV diagram became zero, and beyond that is this surface where it's liquid, dense liquid, and this side is superheated vapor. And this side is solid plus liquid equilibrium, this side is solid, and this is true for a substance that contracts on freezing. Water, as we know, is one of the very few exceptions to this rule, and instead of this curve being here, the rest of the curve is the same. This line flips and comes to the back, and that's what you see in this particular picture at the bottom. Okay, this is the triple line, critical point. This is the shape. This surface little here represents solid plus liquid equilibrium. This is solid. That side is liquid. This surface represents liquid. This surface represents vapor. So this is a surface plot. It doesn't look like a very nice surface. It's a little bit complex, but it is not a full 3D thing in the sense that only points on these surfaces are realizable by that material. This is what is called the PVT surface. Okay, so if you have this surface, we then fit an equation to this, say P as a function of V and T. And then we do something which we didn't look at in very much detail in the earlier part, which is to use thermodynamic relations. I will give out all these details in module 3, the third part of the notes. We really don't need to go into great detail as far as this part goes. It is not part of this basic course. But what it tells us basically is that all the relations that we wrote down are related to one another in some differential form or the other. And it is that differential form that we exploit using this equation to get all the other values of all the other properties. Okay, so that's what we have there. Okay, there are questions. We will take questions. Well, there's just a few more points that I need to make. In making the properties and putting numbers, we need a reference state. And what has been done over the past many years is that we select a state so that values of U, H, S and all, they are somewhat nice manageable numbers, and it's not that all of the numbers are 10,000, 15,000, 20,000. So different materials have a different reference state. For water, we say that at the triple point, HF is equal to 0, SF is equal to 0. For most refrigerants, we say that instead of triple point there, we say minus 40 degrees Celsius, HF is set to 0, SF is set to 0. And for cryogenic materials, hydrogen, nitrogen, oxygen, again somewhere near the triple point, we set it to 0, or for a material like helium, we can reference it to even 0 Kelvin. The thing is that as long as we are dealing with differences of enthalpy or differences of entropy, this reference point does not matter. But if you are going to compare something with water with, say, a refrigerant, where the reference points of entropy are different, then you cannot make the same picture. And I'll show that in the next lecture, how that difference comes in. So we'll stop here and we'll take questions now. Okay, the first question. The question is, if H is equal to Cp T2 minus T1, is this expression valid for all processes or only for constant pressure processes? Similarly for Cv in the case of calculation of written energy volume. I will come to this tomorrow when we look at the properties of ideal gases. Then I will clarify this. Okay, here is the question. Why, okay, please tell us why it is called compressed liquid. I just mentioned that it's called compressed liquid because the pressure at which the water is more than the saturation pressure at that temperature. So we say it is compressed. The pressure, it has been compressed into a liquid phase. That is the reason. Then there is another question. Why specific volume of liquid is decreasing as we are increasing the pressure? Okay. The question is, why are these points going like this when we increase the pressure? If you look at it the other way, by looking at density, when you take water and compress it, its volume goes down. It becomes denser, so density increases. And specific volume is 1 upon density. So you can see there that when you increase the pressure, the specific volume has increased or decreased. The density has increased. That's the reason. Okay, it says we are plotting T versus V. We are plotting T versus V with the help of experimentation results. Yes. But is it possible to conduct experiments at critical pressure and temperature to get various properties? Okay, so the question is, how did these people get all these properties? So what they did was that they took a vessel, evacuated it, and they put a certain amount of liquid in it. This vessel then had heaters around it, and this whole system was well insulated. And in this there were instruments for pressure and temperature. The volume of this vessel was known, the mass of fluid that we put into it was known, and we could measure pressure and temperature. And that's how these experiments were done. So now if you want to create a critical state, what we now know is that if the volume is known, we know what is the specific volume at the critical state, and these two will tell us what is the mass that I should put in this to generate a critical state. Okay, so it's easy said than done. The critical state, at least mathematically, it looks like a singularity, which it is, and at that point almost all the equations that are developed also start ill behaving as differential equations. So now there is a belief that yes, critical point is there, but to exactly get to that pressure and exactly that same temperature and say that it is at the critical state, even within the experimental uncertainties, it's very difficult. But this is the way one would produce a critical state in a substance. Now, having said that, I'll add one more thing. Since this was experimental data, every experimental data has something with it which is called uncertainty. It arises from the basic idea that in this world there is no such thing as exact measurement. So pressure was not exactly measured, temperature was not exactly measured, neither was mass, neither was specific volume, and we quantify how much was the what you may call the error. The limits of error is what is the uncertainty, and in all these experiments, uncertainties in say specific enthalpy is less than plus minus like 0.1 to 0.2%. It is extremely difficult to do such good quality experiments, and that is why we believe those numbers, and that is why you and I use it in solving problems, and professional engineers use that in doing all engineering. But inherently, it is never exact. Okay, what is saturated liquid line? Okay, the question is, what is saturated liquid line? On this diagram, and I have shown TV diagram, and tomorrow I will add on to it and we will make TS diagrams, pH diagrams, any combination of those diagrams. Everywhere we will get a locus of points which correspond to x equal to 0 or which is the saturated liquid. That line which joins all the points of x equal to 0 is called the saturated liquid line. So this line is the saturated liquid line, this is the saturated vapor line. Okay, why does the critical state of a substance occur? Okay, so the question is, why does a substance exhibit a critical state at all? And as I mentioned, this is true of all substances. You take copper, you take zinc, sodium, whatever you have in mind, everywhere you will see these things. But the thing is that this thing happens because you have now increased the pressure to a point where the difference between what is a vapor and what is a liquid has gradually decreased and disappeared. That is what the critical point is actually telling us. So you saw here, below the critical pressure at any point, there was a distinct thing which is called a liquid, where the intermolecular spacing was something. It became a vapor where the intermolecular spacing suddenly increased. This does not happen at the critical point because you have increased the pressure so much that this inhomogeneity that we saw has disappeared. It continuously shows a behavior of one type only, where the intermolecular spacing is now fairly tight and very close, and it doesn't show that it has any ability to become a vapor by getting the molecules very far apart. So that's why this thing happens here. And of course, if pressures are more than the critical point pressure, there is absolutely no hope, because now you have compressed it so much, molecules are so close to one another, they have no chance to get away from each other. How solid, liquid and vapor exist in equilibrium? Okay. So this is a question of how is it that you can have a solid vapor liquid equilibrium, or rather how do we get triple point? Okay, so one word of caution first. When we talk of triple point, or before triple point, when we talk of a solid state, so far I have liberally used the term pressure. Okay, so what it means is that either I have a liquid state which we are cooling and we get a solid, and a liquid we know that if the pressure everywhere will always be constant because it is a fluid. Same is true with a vapor. The pressure everywhere is the same. The moment these substances start becoming a solid, at that point where they have become a solid, the pressure everywhere in the solid is going to be the same. But we know from our knowledge of solid mechanics and stress analysis that pressure is not defined for a solid. So the only thing that we can say then is that if the solid was made at the particular pressure, only at that temperature the pressure inside will be equal to the stress inside, which is the same pressure. If you further cool it, it will not be the same pressure because stresses will develop, and stresses will cause internal average stresses to be different than what the hydrostatic pressure was. In such a situation, if you have a solid in contact with a liquid, the only thing that makes sense is pressure at the surface or the interface of the solid and the liquid. So this is solid, this is liquid, only here it makes sense. We cannot talk of pressure inside a solid, we only talk of stresses. So this is one caution. The second thing, the question is, how come a solid, liquid and vapor can exist in equilibrium? But think of it like this, that you have a vessel into which we put some solid, say ice, around that there is water, we evacuate this. Now we only have vapor in this. And if we allow it to come to equilibrium and we get that pressure here is triple point pressure, P triple point, the pressure everywhere is that and the temperature everywhere is the triple point pressure, then all these three will coexist together. And we exploit this in one very important way, not in thermodynamics but in all measurements of temperature, especially in heat transfer. What we can do is, and you can do this small experiment yourself, take a thermos flask, push crushed ice into it, pack it as much as you can, and then pour a little bit of tap water in it. What will happen? The temperature of the water, which was say at 25-30 degrees Celsius, will go down, some of the ice will melt, and if you keep measuring the temperature by putting an instrument in this, you'll see the temperature going down, it will start going to 3 degrees, 2 degrees, 1 degree. At that point what you do is, you drain out that water, and if you have cold water, or drain out some of the water, or keep that water there and put more ice in it. And then again let it come to an equilibrium. Once you do that, what you have produced is a solid plus liquid equilibrium at 1 bar pressure, whose temperature is 0.01 degrees Celsius, which is the triple point temperature of water. So this is a very easy and a very reliable way to generate a very well-known temperature in a laboratory, and this is an excellent reference temperature. Because any instrument with a thermocouple or an RTD will always require a temperature difference against which you measure a change in a property. Triple point with this is what is called an ice bond. This is a simple and an extremely reliable way of generating 0.01 degrees Celsius. You have in equilibrium solid and liquid. The vapor was at 1 bar, but that doesn't matter too much once you have closed it. So that's how they exist in equilibrium. And in equilibrium, remember, there are three issues that come up here. We have mass of the solid, mass of the vapor, mass of the liquid. And as long as each one of these is in the triple point state, you can have any combination of these masses in this. We cannot just define dryness fraction, but now it's a three-way thing to be defined. Okay, here's the question is, sir, could you explain the importance of critical point in engineering field of application? Okay. Okay, quickly I will do this and I will take it up tomorrow again. What is the importance of critical point temperature? As I mentioned, we are designing, I'm going to jump the gun, tomorrow I'm going to show this. So this is the temperature and entropy diagram. The saturation dome looks like this. If we design something to generate superheated steam, we have to design something that will heat the liquid part. Then we design something that will do the evaporation, where there is a big phase change taking place. The phase change means a big volume change. And then superheating part. So the design of the boiler becomes three-part design. But if you have a supercritical boiler, this will go off like that. Which means I don't need to design three different things, only one thing. And the reason why we design it is that when you use steam at this condition versus a steam at this condition, the thermodynamic efficiency of this or cycle built around this is going to be much more than the thermodynamic efficiency of this cycle. So that is the reason why traditionally pressures have gone up, temperatures have gone up, and we are coming to supercritical pressures and temperatures. The limiting factor though, thermodynamics tells you can go as high as you want in temperature, but we do not have materials for making a boiler that can withstand such high temperatures at high pressures for 20-30 years. That's the challenge. Okay. So with that we will conclude this session. Tomorrow we'll look at some more of the property diagrams, take some more examples, and then we will go on to see what is ideal gas behavior.